Welcome to the part 3 of my video lectures. In part 1 and part 2 of my video lecture, I discussed the formula derivation of internal and external inductance. Now we will discuss the formula derivation of inductance of each conductor in a single phase line. Objectives of this lecture are: learn the philosophies in deriving the inductance of each conductor in a single phase line, learn the physics of derivation, and learn the mathematical method like differential and integral calculus. Our objective of today's lecture is to derive the inductance formula of each conductor in a single phase transmission lines, which is L1 and L2. And this is the formula we are going to derive, where L1 is equal to 2 times 10 to the negative 7 logarithm d over R1 prime, and L2 is equal to 2 times 10 to the negative 7 ln d over R2 prime. Part 1 of my lecture, I discussed the derivation of internal flux linkage and internal inductance, and this is the result. And in part 2 of my lecture, I discussed the derivation of external flux linkage and external inductance, and this is the result. Before we can derive the inductance of conductor number 1, we will first derive the flux linkage of conductor number 1. So if we want to find the total flux linkage of conductor number 1 due to current in conductor number 1, then we need to add the internal flux linkage and external flux linkage. What we did in part 2 during our derivation of external flux linkage, we have assumed two variables, D1 and D2, wherein we enclose the external magnetic flux by two circles with distance D1 and D2 from the center of the conductor. Suppose we have two solid round conductors with radius R1 and R. One conductor is the return circuit for the other. This implies that if the current in conductor number 1 is I, then the current in conductor number 2 is negative I. First, let us consider only the flux linkage of the circuit caused by current in conductor number 1. The current flowing in the conductor will set up a magnetic flux lines. Suppose a line of flux set up by current in conductor number 1 reach a distance equal to or greater than D plus R. It is in this point from the center of conductor number 1. The question is, does the flux link a circuit or the flux inducing a voltage in the circuit? The answer is no, because such a line of flux is enclosing the conductor with opposite current, and so it links a net current of 0 because the current in conductor number 2 is equal in value and opposite in direction to the current in conductor number 1. And it will be cancelled out, and therefore it does not contribute to the flux linkage of the circuit. Now suppose a line of flux set up by current in conductor number 1 reach a distance equal to D minus R2 from the center of conductor number 1, which is at this point. In this case, the line of flux is enclosing only the fraction of the total current in the circuit, which is only positive I. We can say that the flux will link a circuit and will induce a voltage in the circuit. So, between D minus R2 and D plus R2, the fraction of the total current in the circuit linked by a line of flux set up by current in conductor number 1 will vary from 1 to 0. Therefore, it is logical to say that the distance which resulted the flux to link the circuit and induce a voltage are D and R1. Therefore, it is also logical to say that the distances D1 and D2 considered and assumed in deriving the external flux linkages are equivalent to D and R1 respectively. As explained in the previous slides, the distances that resulted the flux to link the circuit and induce a voltage are D and R1, where D is the distance between conductor number 1 and conductor number 2, and R1 is the radius of conductor number 1. This equation is the total linkage of conductor number 1, wherein we add the internal and external flux linkage. During our derivation of external flux linkage, we assume a distances of D1 and D2. Since we already determined the true distances, which is D and R1, we will replace D2 and D1 by D and R1 respectively. By replacing D2 by D and D1 by R1, the equation will become flux linkage in conductor number 1 is equal to 1/2 times 10 to the negative 7i plus 2 times 10 to the negative 7i ln D over R1. To start evaluating this equation, we will notice that it has a common term of 10 to the negative 7i. But I want these two terms to have a common term of 2 times 10 to the negative 7i, and making both terms also to have a logarithmic term of ln. To do that, I will let 1/2 is equal to 2 ln e to the 1/4. To prove that 2 ln e to the 1/4 is equal to 1/2. By operation, this 2 ln e to the 1/4 is equal to 1/4 times 2 ln e. From the rule of logarithm, ln e is equal to 1. Therefore, we can write 1/2 is equal to 2 ln e to the 1. From this equation, we will replace 1/2 by 2 ln e to the 1/4. So the equation will become 2 ln e to the 1/4 times 10 to the negative 7i plus 2 times 10 to the negative 7i ln d over R1. We will notice that the two terms has a common term of 2 times 10 to the negative 7i. Simplifying the equation, it will become 2 times 10 to the negative 7i, open parenthesis, ln e to the 1/4 plus ln d over R1. Simplifying further, the equation will become 2 times 10 to the negative 7i, ln, open parenthesis, e to the 1/4 plus d over R1. But e to the 1/4 can also be written as e to the negative 1/4. So the equation will become 2 times 10 to the negative 7i ln, open parenthesis, 1 over e to negative 1/4 plus d over R1. From the rule of logarithm, ln a plus ln b is equal to ln ab. So the equation will become 2 times 10 to negative 7i ln 1 over e to the negative 1/4 times d over R1. Simplifying further, the equation will become 2 times 10 to the negative 7i ln d over e to negative 1/4 R1. Now let e to the negative 1/4 times R1 is equal to R1 prime. And the value of e to the negative 1/4 is equal to 0.7788. So R1 prime is equal to 0.7788 R1. Therefore, the final equation for flux linkage due to current in conductor number 1 alone is equal to 2 times 10 to negative 7i logarithm d over R1 prime in Weber turn per. Now we will determine the inductance of conductor number 1 by simply substituting the flux linkage of conductor number 1 to the formula of inductance. Therefore, the inductance of conductor number 1 is L1 is equal to 2 times 10 to the negative 7i ln d over R1 prime over I. Cancelling I, the equation will become 2 times 10 to the negative 7 ln d over R1 prime in Henry per meter. Since the current in conductor number 2 flows in the direction opposite to that in conductor number 1 or 180 degrees out of phase, the inductance produced by current in conductor number 2 considered alone are in the same direction through the circuit as those produced by current in conductor number 1. And this will be written as inductance of conductor number 2 is 2 times 10 to the negative 7 ln d over R2 prime. In part 4 of my next video, we will derive the total inductance of the circuit. See you in my next video. Thank you.